Welcome to the 1954 Nobel Prize in Physics, which is really a quantum mechanics prize this year out. It was equally divided between two people, Max Born for his work in quantum mechanics, specifically for a statistical interpretation of the wave function. We'll get to that in a minute. And Walther Bothe, I think I'm pronouncing that right, for the coincidence method and what can be done with that. Now, quantum mechanics is weird, and this video is going to take a little bit different direction than most of the ones I do, because a lot of scientists, including this one, believe quantum mechanics isn't perfect and might have some flaws. In fact, Einstein suggested that all it does is give us a hazy sort of glimpse at something that sits even deeper than what quantum mechanics is supposed to be describing. Now, you've heard the phrase, you've heard quantum loop gravity, quantum this, quantized levels, quantized all kinds of things. What the heck really is quantum mechanics and what's a wave function? Well, let's go figure that out. I'm going to keep the math out of this. We're going to talk conceptually because when you get to the math of this stuff, it gets really funky. But let's dive in and see why it might not necessarily be a perfect descriptor of nature. So Max Born, um, he was said to be instrumental in the development of quantum mechanics. He made considerable contributions into solid state physics as well as optics, a bunch of other things. One of his PhD students was Oppenheimer. He sat on Oppenheimer's committee. But what he really got the prize for was the statistical interpretation of the wave function. It means the long and short of it is it means you only probably know what's going on with the system until you measure it, which is not necessarily the predictive measure that physicists tend to look for. You see the problem that Einstein had here. So Max Born, while he did some great work, he did this thing that does sort of fit, and we're going to dive into it here in a second. But it has its challenges. He also wrote a pretty good book explaining relativity. If you really want to understand it better, it is still available on Amazon. But he was pretty good at explaining things. But the problem I have with quantum mechanics, I think the problem a lot of people have with quantum mechanics is its probabilistic nature. You can only probably know what's going on, and physicists in general, we don't want to go with probably because that's bad. You really want to know what's going to happen in a system. Otherwise, you might make a gigantic mistake. And when you're dealing with nuclear things, you don't want that to happen. You'll probably be okay, is not what you really want to hear. But let's dig into what this wave function thing is, because it's actually pretty important and is usually correct. And does give you certain bounds. But let's dive into what all that gobbledygook means. Now, what is a wave function? Well, this is where we're going to get a little bit funky. Not like George Clinton in the Parliament Funkadelic funky, but funky. Now, in quantum physics, a wave function is just this mathematical way of describing the quantum state of an isolated quantum system. What does all that mean? Let's translate. So let's define a few terms. Quantum physics, the heck is that in the first place? So it describes the behavior of nature at or below the scale of atoms. So if we're talking about one atom or something smaller than that, that is quantum physics. That's where this stuff lives, breathes, and eats, because classical mechanics, Newtonian mechanics don't really apply here. They don't really work all that well. In fact, they don't work at all when you get down to this scale. Now, what is a quantum state? Again, it's a mathematical equation that kind of embodies what we know about that particular quantum system. So it's a funny way of writing a bunch of math that usually comes like a chart like you see there with some funny symbols in it that says, look, there are all your answers. But it really does describe that quantum state. Maybe. Those things are done with a variety of ways. We kind of come into two broad categories. One is using position and momentum variables, and the other is vector quantum states. All that's stuff you don't need to know. But it does kind of give you a way to describe that system mathematically using those two techniques. And again, it doesn't necessarily say, oh, look, your electron is located here. It says the electron might be located there. Your proton might be located there. Now, a lot of this stuff comes into question when you start hearing words like quantum computing, right? And that's, again, going to be a whole different video. But it's not necessarily that you understand completely what's in the quantum system. You understand what's probably in that quantum system, and that's the part that gets a little funny to a scientist, especially if you want to start to do applications like quantum computing. You want to know exactly where your data is and what your data says. You don't want to think it probably says this. You want to know exactly what it is. Now, what is a quantum system? So we talked about what a quantum physics is. We know what a quantum state is. Now, what the heck is a quantum system? Something that can't be defined by classical mechanics. So a quantum system is all that stuff that classical mechanics that Newton did just doesn't quite work right. It can be all number of different things, and there's a lot of funny words for this stuff. So I've got a list of them here. Let me read it out. Superposition, entanglement, wave particle duality, uh, quantization, uncertainty principle, wave function, quantum tunneling, observer effects, and quantum decoherence. All that kind of fits inside that quantum system world. Now, what that means in English is when you get down to this scale, we can't tell you moment to moment exactly what's going on. We can only tell you what we think is going on or what is probably going on or what might have gone on. Now, as soon as you measure it, the theory is everything changes. Now, notice way back when we were discussing one of these terms, we used the phrase isolated system because the moment you look at that system, it's no longer isolated. You took a measurement, you applied something to that system that could invoke a change. So quantum mechanics gets into funky. And the reason Einstein and myself and others are like, there's something not right here, is the world of physics, the world of science wants to know things. We want to know things with a great degree of absolute certainty. I want to know that when I pick up my phone and I drop it, exactly how fast it's going to fall. I want to know that to some great degree. Quantum mechanics doesn't give you that option. It gives you the option to kind of understand it, but it doesn't give you the option to fully understand it. And that is where I and others think it falls apart. Now, does it give you a reasonable description of it? It does. It gives you a reasonable description of it, and you can kind of predict how it's going to go. And it has allowed us to do things that we wouldn't have been able to do otherwise, and understand nuclear processes, and understand photoelectric effect and fiber optics. It lets us understand all those things, but it doesn't necessarily give us a perfect understanding of them. And that is where you hear about things like the unified theory of everything that is supposed to tie all this stuff together, because quantum mechanics is kind of lacking in a few spaces. Now, let's dig into the other part of this prize. So the other half of this prize was Walther Bothe. He got his work for something called the coincidence method. Now, he was an experimentalist who actually got his PhD under a guy named Max Planck, who you heard about in one of the other videos. But he developed his method as a way to study particle physics. And that was something that had been kind of lacking in this whole thing, was a great way to actually get detailed information in the lab. Because it's all great when it's on a chalkboard, but as soon as you put it in the lab, we need to be able to verify what's on that chalkboard is actually kind of accurate. Now, he used a phenomenon of particles passing through detector tubes to generate electricity. So a particle comes through, it generates some electricity, knocks electrons off atoms that are in there, does all kinds of fun stuff. But it generates electricity is the point. And he figured out that if you use two counter tubes connected together so that only simultaneous events register, you get great benefit out of that. So if it detects in one tube, it doesn't matter. If it detects in the other tube, it doesn't matter. It has to detect in both. That's the coincident method because it's coincident on both tubes. Now, what that means is that the detection event had to be caused by a particle originating from a single event someplace, or a particle that was just going so fast that the time in between the tubes was just, ludicrous speed. They'd gone to plaid, as they say in Spaceballs. And that really gave us a lot more information than we used to have. And he used this method to show that energy was conserved when you have impacts in between particles and photons, which is its whole own video, and because photons don't really have mass, right? So how can you collide? But they can, as well as make a more detailed study of cosmic rays than it was possible ever before. But what this method shows you, and what his data shows you, is that the statistical methods brought about by quantum mechanics are typically correct, with some outlier cases that are fringe events, but they still are events and they still happen. The law of randomness does come into play. But the problem with quantum mechanics and even with the experimental setups on it is, you can get the experimental setups to be better. You can more tightly control the experiment, but that doesn't really explain the real world, right? So as you got this really tightly bound set of conditions in a lab, can I predict what's going to happen? Yes, but it's a tightly bound set of conditions. What happens when you put that in an outer space? What happens when you put that in a quantum computer that you want to be able to have millions of people have access to, like we do in cloud computing? All of those things come into a whole different world, right? So that's where quantum mechanics is, in my opinion, kind of weird. in that, and Einstein's too, is that there must be more underneath it. Otherwise, we wouldn't be dealing with probably. We'd be dealing with definitely. We'd be able to predict exactly what's going to go on. Now, until we can get to that stage, quantum mechanics is still going to have people looking at it going, yes, this does describe the situation, but does it fully describe that situation, or does it only give us sort of a glimpse into what's actually lying underneath? And I sit in the same camp that Einstein did, in which I think it really only gives us a glimpse at something that's going on underneath there that we just don't fully understand. And that is the great mystery of physics, is there is more to learn. There's always more to learn. And in the world of quantum mechanics, with it being based on probabilities and statistics, it doesn't seem to fit the mold of, this is the way nature wanted it. Randomness is great, but randomness when it comes to an atom that's just sitting there with nobody paying attention to it, that doesn't make any sense, right? So we need to really kind of get a better idea of what's going on in that subatomic space. But if you remember back to all these other videos we've been doing, even the atomic world, and even now, is sort of 120 years old. We're not talking about anything older than that, and that's if you go way back to the dawn of it. But realistically, the atomic world here in 2024 is 80, 90 years old at best, in some kind of real way, a little bit older than that. But we have a lot more to learn. So we only learned about the stuff we know about across the last 100 years. And it took 300 years in between Newton and Einstein. So we need that next evolution of, let's go one more layer down. Now, will that take big new machines, or will that take all new theories? I think it's going to take both. I'm not sure the machines need to get bigger and more expensive, but I do think the theories need to evolve. And both of those things need to work together, because part of the problem with some of the modern theory is, well, here's this idea, you can never test it, but that doesn't really fit as an actual scientific thing. It's supposed to be testable. So we need to dig deeper, right? And quantum mechanics doesn't really give us the whole picture, and it does give us an answer, and it's usually correct, but it's also based on probability and some tightly controlled set of conditions, which may or may not describe the real world. So that's kind of why I have trouble with quantum mechanics. I mean, I can get the right answers, I can do the math like anybody else, but and I'm sure that's sort of the right answer given the constraints of the equations. But why is it the right answer, and why are we still dealing with statistics instead of exactness? And I want exactness, and that's why we're going to have to keep digging in the modern world of physics into these areas. So we do get to stand on the shoulders of giants, and we do need to learn from quantum mechanics, but we got to go to that next level. And I think that's the important thing that could happen across the next 10 or 15 years. We're kind of right on that edge, I think. But I hope you've enjoyed this video, and we'll see you on the next one.